Online behavior synthesis generates motion by reasoning over future plans at execution time rather than committing to a fixed learned policy. Carefully engineered analytic dynamics have long been the backbone of online planning in legged robots, yet these models are often scenario-specific, possibly tied to physical parameters like terrain geometry and friction. This robot is different. It can reason about its body and motion in real time using a learned model of the world. We do this using a form of learned MPC, or model predictive control, that promises scalability and adaptability. This model is viable for planning across many scenarios outside the data used during training. While policy learning has seen widespread success, learned MPC has been far more difficult to make work reliably in legged robots. This is in part because learned dynamics models often behave well in prediction benchmarks, yet fail when embedded inside an optimizer. Our key assertion is that continuity and smoothness should be a primary consideration when learning models for control, and that many of the failures of learned MPC are not simply caused by inaccurate predictions, but by poor optimization due to a lack of these properties. Standard neural networks frequently produce models that are stiff like the underlying contact dynamics and have non-physical local irregularities. These issues are especially pronounced in contact-rich tasks or regions of the input space where data are sparse. Even when prediction error is low, standard neural networks can introduce unstable gradients and predictions that cause planning to fail. We introduced the Smooth Neural Surrogate MLP, a scalable and easy-to-train architecture that can smooth out non-smooth functions and excels at test time optimization. We use this architecture as the backbone for legged robot dynamics and state estimation, resulting in dynamics that are explicitly designed to be well behaved for trajectory optimization through contact while still remaining accurate to the data. With smooth neural dynamics embedded in an MPC framework, learned MPC becomes practical at scale. The framework can learn variable terrain dynamics and state estimation under domain randomization. In addition to scalability, the framework remains stable and flexible for online behavior synthesis. This means that we can modify costs and constraints at runtime to produce new behaviors without retraining. By prioritizing smoothness alongside accuracy, we enable scalable, flexible, and reliable online planning with learned models, paving the way towards robots that can construct their own models for the world, reason about the future, and solve problems in real time like animals and humans.